All right, what's going on, everybody? We are here on Friday, January 29th. We are going to hit up section 6.6 today. We're going to talk about our graphs of our sine and our cosine function. In general, we want to be able to graph not just sine and cosine, but all six of our trig functions, and we'd also like to be able to graph lots of modifications associated with those functions. So 6.6, 6.7, 6.8 are going to be all of our kind of essential graphing sections here. And I just want to point out real briefly, the way that our book orders them is it sort of, our book suggests that they're going to like introduce sine and cosine, then introduce tangent, secant, cosecant, cotangent, then come back to some slightly more complicated things associated with sine and cosine in 6.8. I kind of feel like that doesn't make any sense. I'm going to do all our sine and cosine stuff like sort of adjacent with each other. So this is just to say we are covering sections 6, 7, and 6, 8 next week, but I'm going to do them in reverse order because I want to talk more about sine and cosine before I move on to our other graphs that it's not, I'm not, they don't not matter, but they matter slightly less. Our sine and cosine graphs are by far our most important ones. So we're going to talk the two sections in a row. So this is just to say one of the few places that will go a little out of order this semester is we're going to go 6.6, 6.8, 6.7, just to kind of keep our sine and cosine ideas together here. So that's just a little bit of logistics right there. So we've really got three videos in a row here that are going to be relating to our graphing concepts here and our properties of these functions that we can see from the graphs. So today's goal, we want to understand what these graphs of sine and cosine look like. We want to understand how to modify these graphs meaningfully, both with their algebraic representations and with the graphical representations. We're going to confirm that the properties of these graphs match the properties of these functions that we identified in our previous video. When we talked 6.5, we identified a bunch of properties like domain, we identified range, period, symmetry. We talked about all these things in our previous video covering 6.5. We want to visually see all those things in the graph today in 6.6. And finally, what our hopefully obvious goal here is to actually model some real world scenarios using our modified sine and cosine functions. And so our final example for today, no, not our final example. One of our examples today is going to be building a more of a model describing a real world phenomenon. We're going to just talk about our weather right here. So that's kind of one of our goals to get out of this thing right here. So what we want to do is we're going to start simple here, and we're just going to look at first our graphs of just y equals sine of x and y equals cosine of x. Then we'll expand them and talking about sort of more complicated transformations of them. When I say more complicated, they're not going to be too crazy. But we want to be able to make adjustments to these for our modeling purposes, for looking at kind of imitating our real world scenarios here. So what I'm going to say is this, even if you've taken an algebra class, trig functions are sort of a different animal than everything else. There's a reason why algebra is one class and trigonometry is another, because even though we're essentially only covering one family of functions, in an algebra class you cover like 8 families of functions, these ones just behave differently. They have the periodicity alone is a kind of a weirder thing. The fact that they're based on angles versus based on rectangular coordinate input outputs is different, right? So kind of what I'm saying here is even if you have good algebraic intuition, it doesn't necessarily mean that you should be able to just visualize what our sine or cosine graphs look like. And so what I'm going to suggest is we're going to do the lamest thing possible here to get started, and we're going to say, let's just do our plot some points version of graphing things. This is kind of one of our early algebra techniques that we always learn is it's like, well, if you don't know what something looks like, just plot a whole mess of points and see if you can complete the curve that goes through those points. This is not always a great technique, but it does work out pretty well for a bunch of our simple scenarios like our basic graph of y equals sine x. So that's the way that we're going to do this first one. I promise we'll do smarter techniques for all of our later graphing stuff right here. The other reason why this is good is because we know that we want to be like learning a bunch of our trig values here that are associated with certain angles. So this graph right here will help us to see if we can kind of remember how do we compute the sine of many different angles that we're going to look at here. So I threw myself down a table right here so we can fill out a table of values and then an axis on which we can go ahead and graph this guy. So what I'm thinking to myself here is x is our angle. I know it's an angle because I'm using x as an input into a sine function. So I'm thinking of x as being our angles. What I want to pick for myself is angles that I know what the sine of that angle is, right? So I'm not going to go pick like just random ones like 13 degrees. That's not helpful to me. I want to pick the ones where I know the exact value here. So let's pick some nice clean ones. We're not going to pick every value that we know the exact value of, but I'm thinking to myself things like, well, 0, and by the way, we're going to do this in radians. 0 radians is a reasonable quantity right here. And I think we're going to hit some, but not all. Gosh, why does it do that little weird jumpy thing? Man, On the one hand, I'm surprised Microsoft Word handles my pen as well as it does. On the other hand, man, some of these jumpy around things are always so weird to me. So pi sixths, pi halves, uh, 5 pi sixths, pi, 7 pi sixths, maybe 3 pi halves, and 11 pi sixths. So I'm getting a bunch of our sixths in here, but not all of them. And then it looks like I missed one box down here. We're going to go all the way down to 2 pi. There we go. I should have just used sticks and not actually used the table right here. So what we should all do is we should all stop and take a minute. If you're watching this video later, you should pause it and you should fill out this table right now, because I know that you can. And even if you can't, you should be able to. So this is a good little, like, take a moment and give yourself a quiz right here, right? So here's what I'm picturing now that you have unpaused the video. I know that sine is always measuring the height of the point on the unit circle after having proceeded through this much rotation. So what I'm going to do for all of my, I'm going to just draw tiny little sketches right here. If I've gone through 0 degrees, then my point on the unit circle is directly to the right. This is our standard angle location starter right here at 0 degrees. I can see that this point has a height of 0. And so that's my first answer. Sine of 0 is 0. And I'm not going to plot all of them right away, but that's going to be associated with our point at the origin right there, right? Now, pi sixth, I know this is like my 30-degree angle right here. All right, I'm going to have to draw a smidge smaller so we can actually see my angles right here. My 30-degree angle is like this guy right here. I can see that sine is measuring height. I know that for my 30s and my 60s, I'm choosing between 1/2 and root 3 over 2. I can see that my height component is the smaller of the two components. The width component is the larger of the two. So I'm going to pick the smaller of my two choices, which is 1/2. Once we get to pi halves, I know that I'm looking at the point that is straight up on the unit circle. So I'm asking myself what the height of that point, and that height is 1 because it's all vertical component there. And we get around to, what am I doing drawing in there? 5 pi sixths. I'm just like writing 5 pi sixths in there for some reason. Once we get to 5 pi sixths, I'm thinking to myself, we're going 1, 2, 3 pi sixths is vertical. 4, 5 pi sixths should be this guy that's right here. I can again see that the vertical component of this guy is the smaller of the two, right? The vertical component smaller than the horizontal component. So I'm again going to pick the smaller of my two choices between 1/2 and root 3 over 2. 1/2 is smaller. And I'm noticing, by the way, that in all 4 of these drawings so far, my point has been on the upper half of the graph, so all of my values were positive. Now, as we cruise on around to pi radians right here, I'm seeing that the height on the unit circle of that point is 0, so I'm going to get that the sine of pi is 0. This point has no height at all. It's at a height of 0 on our axis there. But now we're going to start to rotate around into our third quadrant, where we should finally experience some negatives. So if 6 pi sixths is the same as pi being over here, we want to go 1 additional pi sixth. And so I'm going to be seeing this angle right here. Again, I can see that my height component is smaller than my width component. So I'm going to again choose the smaller of the two values between 1/2 and root 3 over 2. So I know this is 1/2. However, I can see that my height went down. So I'm going to stick my negative on that guy for my negative 1/2. Finally, or not finally, but wrapping around still, 3 pi halves. Well, we've got 0 pi halves, 1 pi halves, 2 pi halves, and 3 pi halves. That's our vertical down point. What's the height of that point? Well, it's gone down 1 unit to get to that point right there. Finally, 11 pi sixths. You should notice that 12 pi sixths is 2 pi. So this is like going 1 pi sixth short of a full rotation. So this should be my guy that's hanging out over here. Again, I'm setting these guys up. Notice I'm trying to pick the nicest output numbers. That's why I picked those as our input numbers right here. I'm again seeing that the vertical component of this is smaller than the horizontal component. So I'm going to again pick the smaller of my two choices for my 30s and my 60s of 1/2. And again, I can see at that point went down. So I should be getting a negative. And for our last one here that I probably should have in the table, 2 pi, we remember that that is coterminal with 0. So it should certainly have the same matching result, and it does because there is 0 height associated with that point right there, right? So this is me kind of like remembering all of my stuff right here. And again, you should be drawing these ever so minimal diagrams whenever you're trying to remember what your things are. I'm honestly not just doing these for you. I still write these down next to all the little evaluations that I do of my trig functions. It helps me miss out on making stupid little mistakes right here. So here's the things I'm seeing. I want to go plot this thing on my graph. Some things I guess I know are that I want my graph to go all the way out to 2 pi. That's my furthest x value that we used. So to graph this thing then, I'm going to see here, that looks like about 1 pi. Therefore, that's 3 pi halves, and that's 1 pi half. I'm also seeing, by the way, notice that this is going to be like a 1 pi sixths, 2 pi sixths, 3 pi sixths is pi halves. Right, that's the same thing right there. So all of my tick marks here is a pi sixths jump. Right? So and that's important because I use some pi sixths out there, right? The other thing I need to know is what kind of y values are we seeing out here? And it looks like all the y values that we see are either 0, 1, -1, 1/2, -1/2. Those are the only ones I ended up with. Now, it's certainly the case that sine is going to have values other than just those 5 numbers that we got right here. I picked these values to be nice and clean on purpose just for the simplicity of graphing. It's the connecting the dots component that's going to get us everything else. Right? So I think that I've at least set up my graph now to be kind of ready for me to plot all these points. I've got 0, 0 already on the graph. Pi sixths, that's this guy right here. Pi 6 is right there. It's going to go up to a height of 1/2. Pi halves has a height of 1. 5 pi sixths, 1, 2, 3, 4, 5 pi sixths. It's 1 pi sixth short of just being a whole pi, is going to be at half. And then we see that sine of pi is in fact 0 right there. Pi gives 0. 7 pi sixths, going 1 additional pi sixth from pi, should be giving me -1/2. 3 pi halves is going to give me -1. 11 pi sixths, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Just as we said, 11 pi sixths is 1 pi sixth short of a full revolution. That's going to give me a -1/2 right there. And finally, 2 pi, we are back to 0 again right there. So it looks like we've got a pretty consistent pattern of all of our dots right here. So I'm going to grab a color here. And now that our graph looks good, I'm going to ruin it by doing a terrible job of drawing a curve through it. You guys ready? Okay, okay. This has gone worse. Hey, that could have been a lot worse than that. That was all right there. So, some things that I want to point out right here before we kind of just walk away from this graph that we made. There's a couple important things. One, we discussed last class that the period of this function is not just, we talked last class that the domain of this function is not just 0 to 2 pi. It's all real numbers. We could keep going. The only reason we stopped right here is because we know that everything's going to repeat every 2 pi. So what we just did right here is one full period, right? If we were to keep going, all it would be is just copying and pasting this graph onto itself and end to end in the left and the right direction forever, right? So this is one representative period of the graph. It's certainly not the whole thing though. This is just being graphed from 0 to 2 pi. I went like this because my table. From 0 to 2 pi as our inputs, as our x values right there. Another really important thing for us to see is that the changes here are very much not linear. And I mean, they're not linear because it's not a straight line, but like, for example, I think that one of the really interesting things to see here is that the sine value starts at 0. And every time I say sine, by the way, I mean the sine function and not the positive negative in the next 60 seconds right here. The sine of 0 is 0. The sine's maximum is going to be 1. How much angle did it take to get to half of its maximum? It took pi 6, or 30 degrees. How much angle did it take to get to the other half of its maximum, right? The rest of the half of the way. We did the first half in 30 degrees. To get the second half of the height, took us another 60 degrees. 2 pi 6, pi thirds out there, right? So one of the things that we're seeing here is this isn't growing at the same rate all the time. It grew twice as fast from 0 to pi sixths as it grew from pi 6 to pi halves. Here it took 30 degrees to grow by 1/2. and then it took an additional 60 degrees to grow by 1/2 again to get all the way up to its maximum, right? So there's just not a constant rate of change over the course of this function out here. It's a curve. Its rate of change is changing all the time. So the good thing that we've done is we have graphed one period of one of our functions, right? So in a sense, that's kind of a minimal thing right here. But if I had to pick one thing that you need to be able to do graphically in this class, it would probably be produce this graph. If there was literally just one thing, it would probably be this guy right here. So pretty important stuff, right? So now this, on our graph here, this only spanned x values, or what we think of as theta values. This little sideways E symbol right here means element of. So this just says where our x values were an element of the interval from 0 to 2 pi. This is just like a domain description right here. This says we only graphed one chunk of the graph. If instead we allowed x, or what we think of as our angle theta, to extend all the way from negative to positive infinity, then we should just get this graph repeating this exact behavior right here over and over and over, infinitely far left and right. So let's go ahead and do that. And then let's identify some properties of this graph that we can visually see in it. And now maybe I could draw some straight lines here today. So what I want to do is identify some points of interest for myself right now. What I'm kind of seeing to myself is that our sine graph, where does it hit the x-axis? Well, it seems to hit the x-axis at every constant or every integer multiple of pi, right? 0, pi, 2 pi, those are all the places that we hit the x-axis, and that will continue on to the right, and it will also be true off to the left. So I'm just going to mark some tick marks here, and in our head, these are all going to be all of our, that's 1 pi, 2 pi, 3 pi, 4 pi, and we can go in the other direction as well. So just copying from up above. I'm just straight up copying right now. I know that these are all locations where we're going to straight up hit the x-axis, all of our integer multiples of pi. I can see from our drawing up above that we're always going to be stuck between this height of -1 to +1. I can see that sine of 0 starts at 0, so it does cross through the origin right here. Sorry, I'm going to scroll one more time here. I can see that we reach our maximum halfway between 0 and pi. So halfway between 0 and pi, we reach our maximum at 1. Then, scrolling up again, halfway between pi and 2 pi, we reached our minimum at 3 pi halves. That's because at 3 pi halves, as an amount of angle, we are pointing straight down. So all of our vertical component is that negative stuff right there. So to copy from above, and in fact what I should do if I'm being smart right here with my colors is to say, that in blue is exactly what we just did above. All I want to do now is just keep on copying that, right? So I'm going to now do a few more copies. I'll leave that guy off with an arrow right there. I can also make some copies going to the left. It's really hard for me to not just make these like V's going up and down as I'm graphing this, and I know that that's a classic problem with drawing this graph right here. I think I did a decent job of that guy right there. It's a little lumpy, close enough. I'd give you full credit if you drew that. I might give you a little funny look, but that's pretty dang good right there, right? So again, the graph does go on forever. Our original one, we just only chose to graph it from 0 to 2 pi, so it sort of like ended at some points. But it's definitely the case that this sort of deserves like arrows on the end, right? It continues going in those directions. So what we did ending of last class is we identified like all of these properties of this graph right here, but we identified it without ever having seen a graph. We identified it by kind of like thinking about the function and thinking about the unit circle. Now we should be able to identify all these properties of sine just by looking at the graph, right? So for the domain, what I can see is this graph goes to the left and to the right forever. And so I would say that our domain here is our negative to positive infinity. The range of our graph is it is stuck between -1 and 1 as its heights right there, right? From -1 to 1. And so I would say that our range is going from -1 to 1 Remember here that we're using brackets to indicate this interval right here because -1 is a value that we get to. +1 is a value that we get to. If it was like up to but not including 1, then we'd use a parenthesis instead. For our symmetry for this guy, this one's a little bit harder for us to just visually see right here. But one of the things I think I can see here, for example, is that if I pick the positive angle here of like pi halves, I get +1. But I'm also seeing that if I were to pick the same angle but negative pi halves, I'm also getting 1, but I'm getting -1 right here. So what I can see for our symmetry right here is it seems like we're seeing things like the sine of negative theta. If you were to instead go in the negative direction for your angle right there, like to that location, that would be the same thing as if you went in the positive direction with that amount of angle, right, out to there, except that we'll get the negative answer out from that guy. So we plop a negative in front right here, and this is what we call our odd symmetry, or rotational symmetry about the origin. All right. And you can tell that if we took that graph and we just rotated the whole dang graph by 180 degrees, it would fall back onto itself again. That's our odd symmetry, our rotational symmetry. It will always be the case that plugging in the negative of an input will give you the equivalent negative of the output of that original positive input right there. For the period of our graph, well, I can look to see where that period is right there, right? What I can see, for example, is if we start at 0, we're going to increase to 1, decrease to 0. Now, 0 to 0 does not mean we've encompassed one full period, because the stuff that's going to follow it is new stuff I've never seen before, negatives. But if we go through all the positives and get back to 0, then go through all the negatives, then now where we start is doing that same thing again. All the positives, all the negatives, right? So one full period here might be right here. However, I do think it's useful for us to recognize that we could identify our period in a different way right here, right? Maybe instead we say, oh, well, our period goes from peak to peak. In this case, we experienced our positives and then our negatives, and then the rest of our negatives and the rest of our positives. Once we start over again, we're just going to do the down and back up again, down and back up again. So this is also one way that we could see that one period of action right there. Or if we started at the bottom right, or right here where it's going to go down, then back up, that would also be one period right there. As long as you're encompassing one full span of all the possible behavior before you start over copying it again, that's representative of one period. And what we can see is things like going from pi to 3 pi, well, that was a width of 2 pi. Going from 0 to 2 pi, that was a width of pi. Going from pi halves to 5 pi halves, that's a width of 2 pi. No matter what way you look at the starting and ending spot, the width of that one period is going to be 2 pi in every single one of those cases right there, right? So recognize that you get choices. If I were to say to you that we have some dilemma with deciding what the period of a graphical function is, any starting and ending spot where you have encompassed the full action of one revolution and then you copy it over and over again, it's always going to be the period. And so recognize that you have choices. Some people feel obligated to only do one of the visual versions of those, and sometimes it's harder, sometimes it's easier. So recognize that you kind of have, in a sense, a choice right there, as long as you can identify the pattern. Where does this graph hit the x-axis? Well, our x-intercepts here are pretty easy, right? This is all the places where our height is 0. It's all the places where the sine of x gives 0. 0 radians, pi radians. 2 pi radians, 3 pi radians. 4 pi radians, 5 pi radians. So it seems like it's all of our integer multiples of pi. So our x-intercepts are going to occur at x equals, and we'll call it here, pi k. It's all the integer multiples of pi is where we hit the x-axis. Finally, the last feature I want to identify here is the y-intercept. Where does this thing hit the y-axis, the vertical axis here? And it hits the y-axis only at one location. That should always be true of any function. And that's going to have a y-intercept right there of 0. And in my mind, I like to say to myself, even though technically this graph goes forever left and right, this function goes forever left and right, I say things to myself, the graph of sine starts at 0, 0. right? That's where it's starting to me in my head, because 0 degrees of rotation provides 0 height on the unit circle right there. Notice that this won't be true of our cosine graph. Cosine of 0 says how much width do you have, and the answer is 1. So the cosine graph won't go through the origin. When we plug in 0, we'll get a height of 1 for that graph right there. So the important thing here is every one of these features right here we identified in our previous video, but we didn't have the graph to look at. Now when we look at the graph, we should see the agreements between the, in a sense, the algebraic properties that we came up with versus the graphical properties, and they all match exactly what we've previously seen. This is good. This is confirming what we already knew from a different perspective. So now let's change what we're looking at. Now suppose that we want to graph the cosine of x. Well, I don't want to do all this work again. That's work right there. Making tables is like my least favorite thing ever to do by hand. I want a computer to build every table I'm going to build for the rest of my life. That's the effort version of drawing a graph. Let's see if we can think instead of do, so that we can produce a graph with less work right here. And what I kind of want to ask myself is, if I look at the unit circle, can I see how all of our sine and cosine values are all going to be related to one another here? And here's kind of what I like to visualize on the unit circle here. All right, so on our unit circle, I think our easiest points to discuss, okay, so I'm immediately realizing I'm going to need a little bit more room because I want to draw some words surrounding this thing right here. So I'm going to give myself a little more room right here. Okay, there we go. Nice and centered. I can write some words. I think that the easiest points to discuss are our axis points here. It's where sine and cosine are always like 1 or 0 or -1. It's always just one component or the other. To get to those points, you either went horizontally from the origin or you went vertically, and you didn't mix and match, right? What I'm seeing over here is that this is the location right here where cosine is going to reach its maximum, right? Cosine equals 1. That's cosine's maximum. On the other hand, sine of 0 equals 0, right? And I shouldn't say that's a minimum for sine or anything like that, because sine goes down to -1, right? So I'm not going to label that. That's an in-betweener right there. For our next one over here, for 90 degrees or pi, we can say that cosine of pi, well, how much left-right component does this point have? It has none. Cosine measures width, right? On the other hand, the sine of pi is saying how much height does this have, and the answer is 1, and that's actually the sine maximum. If I keep going over here, when we're at, that was that's not pi, that's pi over 2 right there. That's pi over 2 is when we're up here. Pi is all the way over here. I was just being dumb right there. Now that we're over here, cosine of pi is asking how much width do we have on the unit circle if we've rotated by pi radians. And that means all of our motion is width. It's -1 right here. We've gone to the left by 1. And this, to me, represents my cosine minimum. It's the lowest cosine ever gets to. And when we look at the sine of pi, we're asking how much height's associated with that point, and the answer is 0, right? We don't have any height at that point right there. And finally, over here, cosine of, I need this, okay, I just need to bump it down right here. Cosine of 3 pi halves. How much width does this point have? None. Sine of 3 pi halves. How much height does that thing have? Sine measures height. All of it's the height, -1. That is the sine minimum. Right? So here's what I'm seeing by doing what I just did right here. It seems like wherever the cosine gets to the maximum, 90 degrees later, the sine gets to the maximum. Then, where the cosine got to a minimum, 90 degrees later, the sine got to the minimum. It looks like these two things are doing the exact same values. They're all just off by 190-degree rotation from each other, the sine information and the cosine information right here. And even with the ones that we didn't label, right, here sine was 0, 90 degrees later cosine was 0. At this point, sine got to its max, 90 degrees later cosine got to its max. At this location, sine was 0. 90 degrees later, cosine was 0. At this location, sine was at its minimum. 90 degrees later, we get back around to the cosine being at its maximum once again right there. So they seem to be following one another, right? They seem to be following each other's pattern. They're just a delay relative to one another up there. So that's saying to me, the graph of cosine should be matching the graph of sine. There should just be like a 90-degree delay in the graph right there, or a pi halves delay in the graph that we're experiencing right there. So I think we can kind of do a mix and match of using our intuition and using our graphical ideas from before of the table. And so I'm going to do my graph of cosine over 0 to 2 pi. And again, let's just kind of walk through a bunch of our points right here. I think I'm going to plot fewer points on here, because I'm expecting the shape to be the same, the general same shape, but its location is going to be different because it seems to be like a shift. It's following behind the cosine graph. Right? So here's some easy ones that I see right here. Those are the four that we identified in this graph. Let's identify those 4 over here. From above, we're seeing that we decided that cosine of 0 is 1. Oh, I already made a mistake. The mistake that I made was putting a point at the origin. There is no point at the origin on the cosine graph. All right, cosine of 0 degrees, this is our x and this is our y, is 1, because when you have done no rotation, all of your action is horizontal. So cosine gets it all, positive 1. By the time we have pi halves, we are now vertical with our point right here. This has no horizontal component, so cosine is 0. By the time we get to pi rotations, this is all horizontal, but it's to the left. So we're going to get our negative 1. By the time we're at 3 pi halves, there's no horizontal component. And back to 2 pi, we know is equivalent to 0. So we should be back to this guy that's right here. So I am seeing the same weaving up and down shape right here. It just seems like we described something more like this. So where I've got this 1 period marked right here, this actually seems to be exactly what we just graphed for cosine. You start at the maximum, we dip down to the minimum, that's at, like for our cosine, that's at pi, and then we went back up to the maximum again at 0 or at 360 right here. So this slice of sine, which started 90 degrees later, is exactly what our cosine graph is going to be. All right, so there, and again, that's just over our 0 to 2 pi, but hopefully you are visualizing for yourself that this guy's going to carry on, and that it's going to also extend the exact same pattern off to the left over here as well, right? So we're getting this repetition. We're still seeing this period out here. And again, for our period measurement, we can still look at things like, that being 1 period right there from 0 to 2 pi. Or we could look at things like minimum to minimum, something like that. And again, we're seeing that went from pi out to, it's going to be 3 pi out there. So again, no matter where you look at the things starting and stopping, as long as you've encapsulated one full experience of its behavior, then that's what we call this 1 period right there. So I do think it's really good to see, not my kind of crappy by hand drawings, but for us to stop and take a second and go over into a computer generated image for where these come from. Every time I'm looking for this, I just go to Google and I ask it for a GIF associated with sine and cosine. Usually gives me some things that are the things I want to see. So I'm going to pop over into my browser right here. I've got Desmos up. I guess I do want to do this real quick right here. If we go ahead and check out y equals sine of x and y equals cosine of x, actually there are some things I want to show you in Desmos. We can see that they are essentially the same shape, but one is following after the other, right? One is sort of a lag behind the other horizontally. Their shapes are the same, their locations are different. They're just a horizontal shift relative to one another. I do want to show you one thing that you should always be doing when you're in Desmos right here. It doesn't help me to have these integer values right here on the axis, because plugging in like 6 into the sine function is never a radian amount that I'm interested in. I'm always interested in these being like multiples of pi. So typically when I'm in Desmos, I'll come over. Oh wait, I gotta squeeze in my screen a little bit right here. So wait, is it going to do this? Oh, it is. Okay. So if you click on the little tool up here, this will give you your graphical settings. The important thing that I always want to do is specifically on my x-axis, where I'm normally putting in like radians, like pi radians, I want my step to be in a unit that's radians. So I'll usually do something like type pi. So notice it's the letter P, but as soon as I type I, it just makes it pi. And I'll usually do like pi halves or maybe even like pi fourths or something like that. This is usually a much, much better visualization for this. Also, maybe these minor grid lines are kind of killing me right there. And also, I know this graph goes from -1 to 1. So instead of on the y-axis going counting by 2's, let's just count it by 1's. I think that this is like a better visual for my graph right here. I can kind of see some more relevant trig expression points on my axes now rather than just integers. And also we can see some nice things. For example, the sine and cosine graphs have the exact same height of √2/2 at pi fourths, or 45 degrees. We can see that sine is 0 at 0, but cosine is 1 at 0. And then that is opposites when we are at pi halves. When we're at 90 degrees, they have switched roles. Here, cosine is 1 and sine is 0. Here, cosine is 0 and sine is 1. So they have flopped their outputs when we have transitioned that pi halves units right there. So I do think that visualizing these both on the same graph is a useful thing to see that they're almost the same graph. They're just following one another right here. It looks like, oh wait, why is that got a 0 right there? It looks like our cosine graph is, well, it depends on which one you visualize the lagging behind right here and which direction we consider it behind. But again, they're a horizontal shift of one another. The other thing I think is really useful for us to do right here, like I just said, is look for the GIF of sine and cosine right here. And if we do this, I think there's two good visualizations that I kind of like to see here. One of them I think that's nice is this guy that's right here. And I know we just get to see a bunch of Google crap. I guess you guys are pretty, is it just going to take me? Okay, cool. A reasonable website right here. Normally this takes me to like outrageous, disgusting GIFs, and it's like some super inappropriate stuff with like a sine graph in between. I'm like, what the heck? So what we can see right here is the relationship between the circle and sine and cosine. So don't just look at this. Stop and focus in on one thing that's happening in this graph at a time. We know that the sine graph in red is always measuring the height of the point on the unit circle. So look at the point on the unit circle and recognize that the height of the point is exactly what's drawing the graph, right? The vertical, I wish I could just click on this and pause it, but I don't think I can do that. But the height of this point is exactly the height of the sine function as time goes on, as this point continuously rotates around the graph. Similarly, the width of this point is being measured by this blue dot going back and forth. We can see the width is to the left, the width is to the right. Now, the only thing it's doing for the cosine is it's reorienting our direction right there, because even though cosine is measuring width, the output of the cosine function is always going to be measured on a vertical axis, even though it's measuring width. So that's why they did that bend right there, so that even though we're getting width measurements, we're still measuring that width vertically. Here we have lots of width, no width, negative width, no width, width to the right, no width, our width is to the left, stuff like that. So if you're looking at this graph, it's good to only look at one color at a time, only look at one point moving at a time. If you just try and like generally look at this, you're not getting really any information from this. Like stop and like focus in on one part of it. I also do really appreciate that they include the theta diagram right there for like where are we at so far in this. But I do wish there was just like a pause button on this, but in any event. The other graph that I think is nice to see with this guy is, where is the other one that I typically see? I think it's this one, is it? No, that's not super helpful. I guess we can kind of see, so this one just kind of does the same thing for us without introducing that bend. The problem with it now is that our cosine graph is oriented sort of in the wrong direction. We still want to lay that cosine graph down on its side so that our input axis is the x-axis and that the output axis is our vertical y-axis right there. But again, it's helping us see that we're following along the black dot as it rotates around, and we're asking what's the width and what's the height of that black dot. And by continuously answering that question, The sine graph is what we get from always asking, what's the height as we traverse the circle? What's the width as we traverse the circle? Right there. Since a circle is like infinitely symmetric, it's not surprising that following the width and following the height produces essentially the same shapes. But since the width starts out at 1, its maximum, and since the height starts out at 0, its in between value, they don't start at the same location, but they do have the same behavior. Right? So I think this is a worthwhile thing to just like, I don't know, find a visualization. That seems to be the interesting thing for you right here. Oh, and we can also see the tangent measurement being thrown into this one as well. Getting a little bit ahead of ourselves, but we're going to see a wildly different shaped graph for tangent once we go to talk about this guy in our second video next week out there. Yep, I think those are just the videos I was looking to see right here. So let's pop back over to our stuff over here. So we've Googled these things right here. It's good to look at some good computer generated images for these guys. So the real deal, though, is that I am less interested in us just being able to, graph sine and cosine, and a little bit more interested in our ability to graph modifications or transformations of these functions right here. Sine and cosine alone are not ever really going to mimic any real-world thing. I'm going to need to adjust these graphs a little bit so that the graphs are representative of a real-world concept, right? So what I want us to do here is to try and graph these 4 functions. And what we all only want to do is just think about how are we changing the currently known graph to get our updated graph. So just before we go on here, notice that this is the graph of sine and this is the graph of cosine. Same shape, but this one started at the origin, sine of 0 is 0. This one started at cosine of 0 is 1. The only way that I remember the distinction between these two graphs is, does it start, like when I'm doing these in my head, I start my graph by doing that, and my cosine graph I start by doing that. I know that those are the tiniest things in the whole dang world right there, but that's all I need to get myself going. I know the shape, I just need a starting spot from which to graph it. Sine passes through the origin. Cosine begins at its maximum value because at 0 radians or 0 degrees, you have all of the width you're ever going to get in the positive direction right there. Okay? So what we want to graph is modifications for each. So notice here, sine on the left, sine on the left, sine on the left, cosine on the right, cosine on the right, cosine on the right. So I'm at least kind of keeping these separated for ourselves. Once we've figured out how to do these, then we'll go and ask ourselves more generally, like, what did we just do, and can we identify some features associated with these graphs here? So let's see if we can do this. So knowing that this is the graph of y equals sine of x, I want to think, how do I change my graph to get y equals the negative sine of x? And the thing I'm thinking to myself here is, we're going to plug in all the same x values here, and I've even lined these up. It's going to go from negative 2 pi to positive 3 pi, negative 2 pi to positive 3 pi right here. The x values are all going to be the same. The thing that's going to change is when we get our output value, we're going to compute the value of sine, but then we're going to multiply it by negative 1. So let's just follow our dots here. When I plug in 0, I used to get out 0. Now I should be getting out 0 and taking the negative of that. Fortunately for us, the negative of 0 is still just 0, so that point is going to remain right there. When I plugged in pi halves, oh yes, and good call. I'm going to talk about that 1 second right here as well. Good call there, Freeman. So when I get to pi halves, my output was 1. I'm still going to get the output of 1, but I'm tacking a negative onto it now. So it seems like we should be getting out negative 1 from pi halves with the function y equals negative sine of x. I got the same value out, but I negated it. When we got to pi, we got an output of 0. To negate 0 still gives me 0. When we get to 3 pi halves, my output was negative 1. I'm going to negate negative 1 to get positive 1. 2 pi gave me an output of 0. Negated is 0. 5 pi halves gave me an output of 1. I'm going to negate it to get to negative 1, right? I think we can see our pattern that's happening. Before we plugged in negative pi halves and got out negative 1, I'm going to negate the output and get a positive 1, stuff like that. So it seems like it's, again, kind of like our same shape right here. It seems like it just sort of vertically flipped us, right? And now I'm going to go ahead and draw a terrible graph right here. Oh my gosh. All right. Let me, that was just embarrassing right here. Here we go. I've noticed that I never look at my Microsoft Word, which is in front of me. I'm always looking at the screen that you guys are seeing, and it's like half the size, and it makes my drawing much harder. Now, in chat here, we've got this comment that is, uh, sine of x is approximately x. The comment is sine of x is approximately the same thing as just x when x is close to 0. And what you can see is that our graph near 0 really just looks like the function y equals x in there, right? If I just showed you what's in that box, it just looks like our 45-degree angle line passing through the origin. Right here, it doesn't look like it's quite at 45 degrees. It looks like it's steeper than that, but that's just because my x-axis and y-axis aren't scaled the same right there. It's not a one-to-one, one-to-one measurement right there. But this is a very, very, very common estimate used in physics. That in a lot of things in physics, we're looking at scenarios that technically involve a sine or cosine function, but if the angles are very, very close to 0, then it's very easy for us to approximate them as actually just being just the input value. That's something that's you shouldn't necessarily expect to be true, but if you go ahead and play in your calculator, take the sine of 0.01 radians, and you're going to get about 0.01 as your output right there. And that's because we're asking what's the height of the graph. As we rotate, we start with no heights, just like we had no radians right there. And as we get small increases in radians, they are going to almost identically correspond to the change in height that we experience. Later, that's not true. Notice that once we're at 80 degrees right here, we can increase by 10 degrees, and we barely increased our height whatsoever. We didn't change our height much doing that last 10 degrees to get to 90 right there. So this approximation is only true near 0. I think physicists generally say within 10 degrees of 0. It's often a casual simplification to just swap out sine of x with just x as long as your angles are only small. That'll rarely be of direct application to us this semester. We're always going to want to think about broader things. But if you end up going and taking physics classes, very, very common substitution to make right there for sure. Good call. So let's do our cosine one right here and then see if we can do some others. So same concept. I want to use guide points. Notice I haven't screwed around with 13 degrees. We haven't seen root 3 over 2 come up or root 2 over 2 come up because I don't want to have to figure out what those decimal values are for getting heights out here. I'm just picking clean points on my graph to help me make some adjustments here. So when we go from graphing cosine to cosine of x to cosine of x plus 1, this says to me we're still going to get all the same values out from y equals cosine x. We're just going to add 1 to the y component every single time we do this. So where I used to plug in 0 and get out 1, I'm still going to get 1 from cosine of 0, but I'm now going to get 1 plus 1, which is actually going to bring me up to a height of 2. I have added 1 to the y value of that point. We're just going to add 1 to the y value of every point. Cosine of pi halves says how much width do you have at pi halves? None. So I'm going to get 0 from cosine of pi halves plus 1 gives me 0 plus 1 for 1. Notice that pi halves used to be at a height of 0. We've added 1, so it's been shifted up by 1. All of our y values are now larger by 1 than they previously were. This should just be a vertical shift upwards right here. So I'm going to keep identifying comparison points right here. That was at a height of -1 at pi. Let's shift it up by 1. So now we're just at a height of 0 at pi. And we can keep on playing this game right here. So I'm just identifying reference points, guide points right here that make this easier for me. I can see our shape shaping up right here, right? So this is just, hopefully you're okay with me using the word of a transformation of our cosine graph right here. It's essentially still the cosine graph. We've lightly modified some of its properties in graphical visualization by making a modification to the equation that we're graphing, right? It's still, we're getting all of our information from the idea of cosine. We're just adjusting all of it by saying, take all your old y values, cosine of x, and add 1 to all of them. So a vertical shift up by 1. Negative sine of x, we saw that this was like taking all the points that were up and making them go down, all the points that were down and making them go up. We saw that this was a vertical reflection across a horizontal axis. Let's go ahead and do a couple more here. Our next one is 2 times the sine of x. Right? So I'm still using this as my reference graph. This is my base case sine graph right here. But now I want to think, what happens when we do this multiplication by 2? Again, I'm going to say to you, we're still going to get all the same outputs from just doing the sine of x part. But it looks like once we've taken the sine of x, we're then going to say, hey, take whatever you got, double it, multiply by 2. So I used to plug in 0 and get just 0. Now I'm going to plug in 0 and get 0 times 2. Well, that's still 0, actually. So it seems like on this graph, 0 times 2, still just 0. But our next point is actually interesting. We used to plug in pi halves into sine and get a height of 1. Now we're going to take that sine of pi halves and get 1 times 2, which is going to be 2. So it looks like at pi halves, we're now actually at that height of 2 instead of a height of 1. We've doubled our height of that point. Similarly, when we get to pi, we have no height, so no height times 2 is 0. When we're at 3 pi halves, our height is -1, but we're going to double that -1 to get a -2. So it looks like what we're doing here is we're taking our sine graph, and now I'm going to get the real bad drawings here, and we are stretching this thing out. All of the distances of all of these infinite numbers, oh wait, I just drew that last one wrong. All of the heights of all of the infinite number of points on this curve are all twice as far away from the x-axis as they used to be. Right? I'm just going to keep on going down here. At negative pi halves, that's the same as 3 pi halves, we were at -1. We double -1 now to go down to -2. So this appeared to be a vertical stretching is what the behavior is that we got out from this multiplication by 2 on the outside there. Right? So this is twice as tall. Now we're going from -2 to 2. Our outputs used to span from -1 to 1. We doubled all of our outputs, so now they span from -2 to 2. That makes sense. I think that this one right here is the trickiest one. We want to be careful with this one right here. So there's still a multiplication by 2, but very importantly, it is occurring inside of the parentheses rather than outside. The very important distinction here is that over here we said we're still going to do the same thing. We said we're still going to first compute what's the sine of x, then we're going to double our output from sine of x. That's not what's happening here. Here, we're saying our contribution to the input into cosine is x. That's what we are giving into the function. Our input of x is going to get doubled first, then the cosine function is going to be getting applied. Right? So if before we were giving it pi halves as our input, pi halves is first going to get doubled to be pi, and now we're evaluating actually the cosine of pi, which is actually going to be -1. You should notice that we used to have to plug in all of the angles between 0 and 2 pi to experience one full period. Since all of my inputs are getting doubled, I only need to contribute just inputs of 0 to pi to get one full period. Because when they get doubled, the span from 0 to pi is going to get doubled to be 0 to 2 pi. Right? So I'm going to say here for x, we needed to see from 0 to 2 pi to get a full period. But with 2x, we only need to contribute 0 to pi. Because when I'm plugging in 0, I get cosine of 0. I'm going to get everything in between all the way up to the cosine of 2 times pi once we're throwing that guy in there. So what this says to me is that since our contribution is going to get doubled for us, we only have to contribute half as much. So again, This is like me saying, here's how I explain this when I'm teaching my algebra class, right? Imagine that this cosine function is you purchasing groceries at the grocery store. Suppose that you are going to the grocery store and your significant other says to you, hey, listen, you need to come home with $60 worth of groceries. Typically, you bring $60 worth of groceries to the grocery store, you make a purchase with that $60, and it results in you having $60 worth of groceries when you leave. The difference now is that you are going to come to the grocery store with some number of money, but what you know is that there's going to be some crazy dude. We're in Humboldt County. There's going to be a crazy person. There's going to be a crazy person that's standing outside the grocery store. Well, okay, this is the opposite of Humboldt County. And he's going to double your money as you walk in before you make your purchase, right? The 2 times x happens before the cosine is applied, right? The cosine is the purchase, right? So I'm saying to you, if you need to come home with $60 worth of groceries and somebody's going to double your money before you walk into the store, how much do you need to bring to the store? Don't let that 2 times x think to you 120. You can get away with only bringing $30 to the store because somebody's going to double your money as you walk in, and then you're going to make a purchase with double that money and leave with the same thing that you were originally coming with. So this is saying because we are doubling the input, we can get away with only contributing half as much input to still experience the same result overall. Right? So half the input for us is going to be a horizontal compression here. Right? So whereas before on my cosine graph, I needed to go, so I guess I should say, when I plug in 0, it's still the cosine of 0, and that's still taking me to my height of 1. But we used to have to go all the way to a contribution of pi to get to a height of -1. I can now get away with contributing only half as much of that to get the same result. So I'm only going to contribute pi halves to get to that -1 instead. Right? Because if you plug in pi halves into this expression, 2 times pi halves is pi, and the cosine of pi is us pointing to the left. That's our -1 right there. So we're going to continue to see this kind of thing right here, where we're going to go more rapidly back and forth. Wow. For all my graph complaining, that went really smooth right there. So notice that this thing has been like compressed by a factor of 2. We smashed it down. Yes, this is an alteration to our frequency. Our frequency is twice as much because our period is half as long. I'm going to write that sentence. Right? Notice here that if we go like from peak to peak, we're experiencing 1 full period, but it only took us 1 pi to do it now. So we have changed the period of this trigonometric function by using a constant multiple on the inside. That's going to be really important for us here in 1 second. Right? Good call with that frequency comment right there. We haven't defined frequency yet, but I think frequency is a really natural thing to think about. We all have like a non-academic, at least, definition of frequency, I think, in our heads right there. And so this was I'm going to label this as a horizontal compression by a factor of 2. Meaning we're only half as wide. So, by the way, you should notice then, if we did something like cosine of 1/2 times x, now we're in our true eureka situation where somebody's going to take half of your money from you before you walk into the grocery store, so you need to contribute twice as much. If you need to leave with $60 in groceries, now you need to bring 120. Somebody's going to take half your money, then you get to make your $60 purchase right there. Yeah. So those are the words right there, and then our midline is going to be our other word that goes with that one in the top right. So in chat, I'm getting our word that describe these properties that we're modifying. Let's go name all these right here. We're going to get our amplitude, period, midline, phase shift are our four things that we're going to talk about right there. All right. So why might we want to consider these types of transformations? We can use trig functions to model real-world scenarios that experience both fluctuation and repetition. And it turns out there's a huge number of things on Earth that we care to model that experience both fluctuation and repetition. And so these are going to be the baseline functions that we want to use to modify to fit our real-world phenomena phenomena out there, real-world things that we experience. So suppose we would like to model the temperature of one day in Eureka, where the temperature fluctuates from 55 at the lowest to 65 at the highest. What function should we use? Well, I'm picturing to myself here that we are going to span from a low of 55 to a high of 65, where right in the middle there should be a 60 right there, right? So what I'm picturing to myself is I want to come up with some sort of trig function that's doing something like this, right? That would be a reasonable temperature model for one day right there. So what I'm picturing here is with this guy, it seems like our trig function is no longer centered at a height of y equals 0. So I'm going to scroll back up here and look. When we played this game with our cosine function, typically our sine and cosine graphs are centered at a height of 0, right? There's that midline that we're seeing that has a height of y equals 0. Well, notice that by adding 1 to the end, it's shifted everything up by 1, and now the midline of this graph is at a height of 1. Therefore, in our situation over here, it seems like we want a sine or cosine graph where we're adding 60, so that the middle is at 60. So maybe something like sine of x plus 60. Now, what we know is that the sine function is going to go up by 1 and down by 1. That's not quite what we want. We want this thing to go up 5 and down 5, right? Our typical sine graph only increases by 1 from its midline and decreases by 1 from its midline. I'm visualizing our y equals 2 sine x scenario here. I know that when we multiplied by a 2 on the outside of the trig function, don't confuse this 2 on the outside with this 2 on the inside. I'm going to shake my fist at you many times about that one. But here we saw this constant multiple of 2 on the outside stretched this by 2. So instead of only going up 1 and down 1, we went up 2 and down 2. In our case right here, we want to go up 5 and down 5. And so I think I can just go ahead and slap on a 5 sine x, or 5 in front of this thing right here to say we want to shift the whole thing up by 60, and then we want to go up 5 and down 5 from our midline right there. All right. So I think we should stop right now, since that was kind of a heavy piece of math right there for having just introduced these graphs. Let's go take a look at Desmos and see what Desmos thinks about this guy right here. All right. So come back over to our browser. I'm sort of saying, and I'm not even thinking about sine versus cosine at all right now. I'm just picturing, I don't know, pick one, right? So the first thing I did is I said, well, let's add 60 to this thing. Somewhat unsurprisingly, this graph is gone, but that's just because it's like way up here now. I've shifted it up by 60. The good thing that this did is it did make it so that our graph is now centered at a height of 60, but our bad thing is that this suggests that our temperatures are only going to go up to 61 and down to 59. And that's crazy. We have way more temperature fluctuation than that in Eureka. There's my joke for the day right there, okay? So we want to experience this thing to get bigger. And in fact, I'm going to do a nice little thing right here, and I'm just going to put an A right there. If you're not familiar much with Desmos, Desmos is cool with you taking in an unknown parameter right there and giving you a slider bar so you can adjust its value. Notice that as we make A bigger, it does more and more of this stretching right here. We saw that we wanted A to be 5, and there we go. So now it looks like we are getting these temperature fluctuations to occur just kind of like we thought, right? We're going to have our temperature is going to span from 55 to 65, and as it should, every day we're going to experience about that same thing. It's true that this is not a perfect model, but I think this is in the ballpark of how we should normally experience temperature. So like this slider bar is your friend right here. Use stuff like that, and I'm going to show you the the extra awesome use of this in a minute, that it can do multiple of these at once. So Desmos is your friend. If you already know this, you should be saying like, yeah, I know, it's awesome. And if you haven't seen this before, then you should be saying, holy crap, that's awesome. So do stuff like this. It'll give you these slider bars right here. So I'm just going to make that the 5 that we know that we actually want that to be right now. So is this good for us? Well, I think that we did some good stuff and some bad stuff here. The reason that I think that this is good is because I'm trying to get my like proper viewing window here. The reason that this is good is because this now does span temperatures from 55 to 65 and it repeats them just like we want. The reason why I don't think this is very good is because I don't know what the heck these x-axis values mean to me down here. 5 pi, like what's that really measuring for us right here? When I think about this, what I'm visualizing for myself is I think that this one full up down right here should be like a day. What I want to have happening is that this vertical line right here, this should represent the start of a new day, and we experience the same up down of temperatures for that next day again, right? Currently, what we have is that 0 to 2 pi is one full period, but I kind of feel like I want that to be more like a 24-hour thing so that I can plug in a time hour and predict a temperature from this thing, right? So I feel like I want to adjust the period of this graph as well. I don't like 2 pi being one full period because 2 pi what? I want 24 to be the period so that I can say 24 what? 24 hours. That's how often we repeat our daily temperatures, right? So let's pop back over to Microsoft Word here and say exactly that. This seems like a good starting spot for my model, right? Now let's consider that we're measuring time in hours. We want to repeat with a period of 24, not with a period of 2 pi. Sine of x has a period of 2 pi, and we haven't modified it at all. Scrolling back up, I'm remembering that we came up with a way to modify our period before. We're going to need to do a little bit more of a complicated period modeling situation here, but I think we can do it, right? So here's what I'm seeing for myself here. Sine of x has a period, so I'm going to say our y equals, and then our period is 2 pi. We saw things like sine of 2x has a period of only 1 pi. So I know that multiplying by something makes my period shorter. Overall, I kind of want to make my period longer, but one of the things I'm noticing is that pi keeps on showing up in here, and that's kind of really aggravating for me. Maybe I can think to myself, I don't want there to be any pi in my period at all right here. So I'm thinking maybe if multiplying by 2 inside divided our period by 2, I could multiply by pi on the inside now, and that should divide our period by pi. Notice that you only have to give the span of x contributions from 0 to 1 to result in experiencing all of 0 to 2 pi inside of sine, and therefore it should have traversed one entire period right there. Now, we're close. I know that multiplying by stuff on the inside makes our period shorter. That's what we've seen here. We went from 2 pi down to 1 by multiplying by more and more and more. Therefore, I'm thinking I can divide inside of my sine expression to make the period longer. How much longer do we want to make it? Well, I want to make it 24 times as long as this, so that our period is 24 hours. So I'm thinking to myself, sine of 2 pi over 24, and this should have a period of 20, oh, not 2 pi. I was writing the right thing, and in this class, I can't help but write the letter pi after the number 2. So this is our slick way to rewrite our new desired period. And so you should notice that this is a general rule. We're going to state this rule generally down below. I'm going to verbalize it right now. To make a sine function with any period that you want, all you have to do is multiply on the inside by 2 pi divided by the period that you want. This has a period of 24 because this is sine of 2 pi over the period I wanted of 24 right there. So let's go to Desmos and just graph only this function and then incorporate it into this guy, the thing that we're trying to like build, right? So this says to me that we really want 5 times sine of 2 pi over 24 x plus 60. This is my updated model that I now think is going to give me hours on my x-axis. So I'm going to go to Desmos and let's just do the sine thing, then we'll go back to our model here. So I'm going to make a new one. And in fact, I'm going to do this. I'm going to make it A. I'm going to add a slider bar for A. And what we should be seeing down here is that when A is 1, we have a period of, well, it looks like about 1. And in fact, in this case, I'm going to get rid of this being in terms of pi right here. And look, we see exactly this. A is the period. 2 pi over blank. Blank is the period of your sine function right there. This went up and down and back up. It experienced a period of 1. If we made a like 3, then now it takes 3 units for us to go up and down and back up again. We can, oh my gosh, I'm sitting here not on the thing. Sorry. I'm going to start that last 2 minutes over again right here. Here we go. I'm going to come over to Desmos now. I've been looking at it on my screen and I didn't bring it over to your screen. In Desmos over here, I'm going to type in this 2 pi over just a right here, right? Because I'm going to let that be my, what I think is just my period term. I'm noticing here, by the way, I changed my x-axis over here to not be in terms of pi anymore, just in terms of 1. And I'm seeing that if a is 1, I think that's just my period right down there, and I do see that. It takes 1 x span to go up, down, back up again. If I make this longer, like out to 3, it now takes 3 units for us to go up, down, back up again, stuff like that. I could make it awkward fraction amounts, right? 3.4, up, down, up again, in 3.4 units is how long it took us to do that guy right there. So I feel comfortable with this setup that I made. 2 pi over whatever you want your period to be will give you your desired period of that sine function right there. Multiplying by the 2 pi scaled us down to a period of 1. Dividing by a stretched it from 1 out to whatever you wanted it to be. So let's incorporate that into our actual model of interest here, right? Currently up here now, we have this thing that is, like, I don't really understand what our x-axis is measuring here. But now if I instead make this 2 pi divided by 24, then now I'm seeing that this is actually more representative of a day. I'm going to get rid of this guy right here. Now I can see, and maybe we should make this intervals, that's not what I wanted. Intervals of, like, I don't know, on the x-axis, like, let's make it like every 6 hours or something like this. I think this will be visually much, much better for us here. Now zooming out, and oh man, this is getting real nice here. So now notice that over a 24-hour time period, that's this vertical line right here. Here we are at 24 hours. We're back to being, right? We've experienced 1 full period in 24 hours. This is getting really, really close to an actual model for looking at temperature over the course of a day now, right? By making modifications to the sine function. Now, the only thing I still kind of feel like I have some beef with is where do we start and where do we go from there? I think it's pretty typical, especially if you're a person that uses like military time, that time 0 should be representing like midnight, right? And we should be progressing through our day so that time like 23 is like 11 p.m. I don't think that from midnight to 6 a.m. the temperature increases the whole time. That doesn't sound like what happens. In fact, it sounds to me like the opposite is true, right? I feel like at midnight is when our temperature is decreasing, right? Stuff like that. So let's now go back and take one last look at this thing to update our model one more time. So I feel pretty good about our update right now. Finally, let's make it so our temperature should be at a minimum at 6 a.m. and a maximum at 6 p.m. That's not quite how that quite works here, but it's pretty close. And also, I should say, the reason that you probably disagree with that is because it's January right now. We have more hours of dark than we have of light, so it's not evenly balanced. But if we walk out into, where we experience our equinoxes in the spring and the fall, where we have equal hours of sunlight and daylight, then it should be much more representative of our symmetry that we experience with the sine graph right here. So currently, we have sine of x, and I'm not including all of our modifications, but we know that sine starts at the origin, gets bigger, and goes smaller. What we want is a mystery function, but what we're thinking is that starting at this time, we should go down to get to our minimum at 6 hours, right? That's going to be 6 a.m. We should go back up at noon to be at our midline, and we want back up here at 6 p.m. That's our 6 a.m. And this is our 6 p.m. to be back up at our maximum right here. Well, this looks to me like it's still sine, because it still goes through the origin. but we want to vertically flip. And so that tells me, I think our pretty dang good weather model here for Eureka is -5 sine of 2 pi over 24x plus 60. I think that's a pretty dang good representation of what the temperature is like in Eureka on an average day out there. Right? That's pretty cool. We can make modifications to things that experience repetition. Modifications. We just used all 4 of the modifications from up above. We vertically stretched with the 5. We vertically shifted with the 60. We horizontally stretched to change the period with the 2 pi over 24. And we did a vertical flip just to agree with the fact that we thought that our temperatures should decrease at midnight till 6 a.m. rather than increase at midnight till 6 a.m. You should also notice it was possible that we could have said something like, oh, temperatures reach a minimum at midnight. Well, if they're at a minimum at midnight, that says to me we would maybe use the negative cosine function instead of the sine function. I just started using sine up there, but we might have changed our mind and wanted to use cosine right here instead, because negative cosine experiences a minimum at 0. Because at 0 we get cosine as 1, but if we're doing negative cosine we would get -1, its minimum value at the time 0 right there. So that's our last step, was sort of making our plus or minus sine or cosine consideration. We chose to stick it out with sine, but we did want to flip it to get the agreement that we wanted with our temperature considerations right there. So super cool stuff that we can do with this. So let's generically see like the broader strokes of what we just did. We'll identify some graphs and we'll call it a day right here. In general, the shifts, the transformations that you should expect to deal with here are typically shifts, stretches, and reflections. There are other families of transformations. We're not going to quite talk about them. Our horizontal shifts are going to occur when we make horizontal adjustments, our adjustments to our input. Our input is our x values. Adding or subtraction will do horizontal shifts. This one that I have highlighted right now is the one that we haven't talked about today. It's going to be in the next video. This is our vertical shift right here. So I could say this is our horizontal shift. This is our vertical shift. We did this one. That's our plus 60 right there. Some stretches. This was our horizontal stretch or compression. And that's because the A was on the input to the function, so it adjusted our input values, versus the A on the outside was affecting the outputs from sine, so it affected our output values. So that's going to be a vertical stretch or compression. Finally, we saw that applying some negatives can affect a reflection here. This is the one that we did where we said, take all of your outputs from sine, the outputs, the vertical things, and flip them, right? Take the negative of all of them. On the other hand, if we would have attached a negative to the input, that would have said, flip all of your x values. And so that will give us a horizontal flip over the y-axis. So these are the general families of shifts we should expect to experience. I wrote them in terms of sine. This is true for like literally any function that's a function, not just sine, not just trig stuff. I just wrote these here because this is the format we've been kind of used to seeing it right here. Right? So let's go ahead and name each of these things that we've already seen, do 2 examples, and we'll call it a day. Right? So in general, our amplitude is the distance. Okay, I'm immediately realizing I want to flip a bunch. I want to move a couple of these around here. So, trigonometric transformations, sine and cosine have enough in common that we typically collectively refer to them and all of their transformations as sinusoidal functions. So that says to me, cosine is a sinusoidal function, and so is sine. Tangent's going to be different, right? But sine and cosine and all their transformations are collectively verbalized as the sinusoidal functions. All of them have these properties that we're about to describe. Okay, I'm going to just write this one in words right here. Our letter that's often used for the midline, doesn't really matter, is k. But we're saying here that when we graph our sine and cosine functions, right, that our midline is exactly this guy right here for sine of x. Right? We did our cosine of x plus 1. And when we graph cosine of x plus 1, this guy was looking like this guy right here. This had a midline of 1. And so our midline we can always describe as our sine of x plus k. That's always going to describe where the midline of our graph is. It's the center of that sinusoidal up and downing that we're doing right there. So putting a plus k on the end is going to be our vertical shift term. And if k is negative, that just means go down. That's all that's doing there. The reason I shifted these around is because it's hard for me to define amplitude without using the word midline. This is the distance our graph goes up and down from the midline. Now, base case graphs, amplitude of, this we'll call capital A, of A equals 1, right? Typically, from the midline, our sine will go up to 1, and it'll go down to negative 1. It's sort of like a radius, but it's not a circle, right? But it's our distance from the midline, right? So we can do things like sine of x. Looks like this guy here, right? And we know that it's got a midline of 0, and it's got from top to bottom heights of 1, right? This is a gap of 1, and this is also a gap of 1 that we're experiencing right there, right? That's negative 1, 0, and 1, right? The height from the midline to the edge, to the maximum or the minimum, should always be the same, and that measurement is what we call the amplitude. The other one that we did was like 2 sine of x, and in this case right there, it's like the exact same picture right here, right? We just went twice as far. And in this case right here, we went 2 in each direction. That was our negative 2, 0, and 2 values right there. So in general, we say that A sine of x, this is our amplitude term. So these were the two adjustments outside of the trig function, adding outside and multiplying outside. Our next two adjustments are adding inside and multiplying inside. That's our period. We saw that to adjust the period, we multiplied inside of the function. Base case, this is a period of 2 pi. So we saw things like, we know that sine of x does its, this goes to pi, this is at negative pi, and we can see that that width right there is 2 pi. That's our period right there. More excitingly, we saw that our sine of 2 pi over 24x had a period of, and this guy went like, you know, we got our up and our down right there, and that was out there at 24, right? So it seems like we can identify what is the period of our graph by looking at the coefficient sitting in front. Notice that's a 1, right? So sine of, let's call it 2 pi over p. P is the period. Right? Notice in this case right here, Notice that when we're just talking about the graph of sine of x, you can kind of stupidly think about this as the sine of 2 pi over 2 pi x, and consequently the period is 2 pi. Right? I can see it right there. That's just 1x right there. So it's kind of I mean, you should never write that for yourself, but this is just our justification that even our simplest case follows this somewhat difficult rule right there of 2 pi over a constant. That constant on the denominator is the length of one period of a graph that we've seen right there. Finally, phase shift. I'm just going to leave this one alone. This is the one that we're going to talk about coming up here in our next class period here. So in general, what we do want to come up with is the fact that we can make all sorts of these modifications. I want to come over to Desmos and show you something that's super duper duper nice that you can do here. If we go over to Desmos and think about these ideas now, I'm going to just turn off that really nice graph that we made here. What I can do is literally just give Desmos all this stuff. Our amplitude is A times the sine of 2 pi over P times X plus K. Notice it gives me an option to add a slider for all three of those parameters that I've just plugged in there, the amplitude, the period, and the vertical shift. You can just add sliders for all of them. Now, it's kind of hard for me to see this. Let's go center ourselves at home here. It always starts you off with values of 1. Our typical scenario is to see an amplitude of 0, a period of like 2 pi, which is going to be hard for me to get in, it's going to be about right there, and our vertical shift of 1. Is it doing this in degrees now? Why is it being weird with me about the P? Wait, what the heck is it doing? Oh, sorry. I made my amplitude 0. Sorry. I wanted to make my amplitude 1. I meant to move the midline to 0. That was just me being dumb right there. There, now the midline's at 0. Notice that shifting the midline K is just a vertical shift term right there. Just slides the whole thing up and down. Amplitude is a stretching term, but notice that the amplitude is a stretch from the midline. That's really important right there. Also notice that when A becomes negative, we see our vertical reflection happen. Now this is a vertical reflection of the sine graph right there. And again, we can make our period be longer. That's going to stretch it out further. Or we can make our period very narrow so that we get a very high frequency with a very short period right there. A period of only 1 instead of a period of 2 pi. That's less than 1/6 of what the period used to be right there. So recognize that you can just throw a super generic graph into Desmos and just play around with your slider bars until you've arrived at the graph that you are interested in doing right here. You could almost just not actually know about what these things are doing and still play around with your slider bars to get the rest of the way, and you're going to be good to go. Right? We will include one more parameter into this thing other than the A, the P, and the K next week. It's kind of the bummerest one to deal with, which is why it's going to be saved for 6-8 instead. It's not too bad. It's still going to follow around our same concepts here, but I approve of their decision to leave it in a later chapter. So let's just graph a couple things here and call it a day. I know this is slightly long here, but I think it's worth it to see some examples for this guy. So let's draw 2 graphs, and then we'll identify one graph, and we'll be out of here. So some things I'm thinking. What is my order of thinking about this? I think, like, I know that you guys can just type this into Desmos, and I'm just highly uninterested in your ability to type in this. I am interested in your ability to just say, yeah, I know what that graph looks like, and just graph it by hand, right? So here's my order of thinking about this. Step 1, graph the midline. I know that our graph here, in fact, well, okay, yeah, I'm going to... So I'm going to go to my height of 3 right here. And that height of 3, I know is the midline that our graph should traverse. From the midline of 3, I know that our graph is going to go up 5 units. That's our amplitude, and down 5 units. So I'm going to go up 1, 2, 3, 4, 5. And I'm going to go down 5. 1, 2, 3, and I need to go down 2 more. Right, 5 units in each direction from the midline right there. Right? I've dealt with the 5 and the 3. Now I just want to graph the sine function as passing through this as its midline and with this as its bounding points. I know, and again, when I think about the sine function, all I do when I'm graphing it in my head is I just do like this for my, okay, that was a bad one right there. I just do basically this, right? And it's kind of like we said earlier, it's like it should be the one that kind of looks like the y equals x function going through the origin. And so I know that this guy is going to, when we plug in 0, sine of 0 is 0, 0 times 5 is 0, but plus 3 gives me 3, so I'm at a height of 3. I know that this thing has not had its period adjusted at all right there. So sine of 0 is 0. Pi halves gives me our maximum. Going out to pi gets me back down to our minimum, or to 0. And then going to 3 pi halves gets me down to our minimum. So it's actually going to be like literally on my writing right there. So from here, I think I'm going to go up to our max at pi halves, back down to our baseline at pi, and then down to our minimum there at 3 pi halves. Ugh, that got gross right there. Anyway, we are at negative 3 pi halves right there. Remember, negative 3 pi halves, that just says rotate 3 pi halves in the backwards direction, which is going to bring us back around to our vertical thing. 3 pi halves gets us around to here. That is when sine is positive 1 is its maximum right there. So that's why we're getting 8 at that location. That's right there. Right? So kind of a tough graph right there, but we are getting up to this value of like y equals 8, of y equals negative 2. That's our y value of 3 right there, and I've marked some x-axis values to help me really see where some of these values are happening at. So I know that my graphs always kind of look bad by hand, but hopefully we can agree with how we built that graph, how we know what that looks like. Let's do this for our cosine graph over here. So I'm going to be a little bit smarter. In this graph, I built a graph that was like symmetric in every direction, but we really only mostly needed the top half. I'm going to stop and think about it with this one. This graph has no vertical adjustment, and it does not have any vertical stretch. This graph is going to live between negative 1 and 1, so I think I can, basically what I'm saying is I don't need all that vertical height to go along with this right here, right? I think I can graph this a little more simply just like that and give it maybe more width instead. What I can see are the two things that are going to happen is we're going to get a vertical flip, and I've seen that we want to be able to think about our period as 2 pi over p is going to be, right? We want to know what actually is the period, right? So I'm going to do a little bit of algebra here. 2 pi equals 4p. I multiplied both sides by p, and now I'm going to divide by 4. 2 pi over 4 is the new period, and that's really just pi over 2. So it looks like we used to have a period of 4. We only have 1/4 of the period. When you walk into the grocery store, somebody's going to quadruple your money. So you only have to bring 1/4 as much. We're only 1/4 as wide as we used to be, right? So before we were our cosine graph. Okay, all right. So let's start with a point to start from. If I plug in 0, cosine of 0 is 1, but we're going to take the negative of it, and we're going to get negative 1 down here, right? So I know that my midline, I'm going to just put a couple side ones right here, right? Our k is equal to 0. Our amplitude is equal to 1. Those are unexciting. Those are same as our base case graph right there. But in this case, because the negative cosine function, I've vertically flipped it. Cosine normally starts at its max. This one's going to start at its min. From here, I know that we're just going to basically do some cosining behavior. I think it's easier for me to graph this one and then label the x-axis afterwards, right? I think that's going to be my smarter technique for this. This is a height of 1. This is a height of negative 1. And now my question is, where are these points? Well, I know that this guy right here has to just only be pi halves because this is our 1 full period. And so we might identify things like we reach this maximum right here at pi fourths. We reached our first x-intercept here at pi eighths. Our second one here at 3 pi eighths, stuff like that. So I can identify a bunch of the appropriate x-axis locations there by understanding what one period is and then just breaking them up into some fractional amounts that live out there right now. When I ask you guys to graph some of these by hand on your homework, I am absolutely going to say that you need to graph like 12 evenly spaced values on the x-axis so that it's very clear where they are. Mine are coming about a little bit crappy right here. Yours are going to be cleaner because you're going to take more than 30 seconds. I'm trying to like get through some more strategizing rather than the artistic component of this that's right here. But recognize that you want to pick apart what every single one of these modifications is individually telling you. 5 out front is a vertical stretch factor. Addition of 3 on the end, vertical shift factor. A negative inside or outside is a flip. Since it is outside, it's flipping our y values. Our outputs got flipped. Multiplying by 4 on the inside should be a vertical stretch or compression. We can do a little bit of algebra to determine the new period that we're going to get based on having that constant multiple. Thinking that our constant multiple in front of x should always be thought of as a 2 pi over p. We had 4. We solved for what period that is associated with right there. All right. Last example of the day, I promise on this one, determine the equation of this graph. Here I'm saying to myself, and by the way, if you're watching this video, you should pause right now and do it for yourself. It's our great little like quiz time for ourselves, so do that. Great, now that you've unpaused the video right here, I'm going to identify our low to high and our midline, right? Wow, can I draw a less straight line than that? My goodness. Oh my goodness, oh my goodness, I can't wrap this up. Okay, there we are. So I can see that we're going to go from y equals 1 to y equals 7. And I ask myself, what's halfway in between those two? Well, I can find their average. 7 plus 1 over 2 is 8 over 2 is going to be 4. That might have been unnecessary math for right here. I promise you next week we're going to get some situations where you actually probably are going to have to do a little computation to find what's halfway in between. So I think that this should be my midline. Should be k equals 4. I think that my amplitude here is the distance from the midline to the amplitude. Yeah, right? Yeah, that seems good right there, right? My amplitude is 3. It's the distance from the midline to our edges. It should be the same on both sides. So I know that I'm looking at now. I guess what I've figured out so far is based on this information, I'm looking at y equals, I haven't decided if it's positive or negative. I haven't decided if it's sine or if it's cosine. What else do I see out here, by the way? I haven't decided what's going on with our period coefficient right there. But I do think, I do think that the pieces that I know so far are that there's going to be a 3 right there for our amplitude and a plus 7 on the end for our midline, right? That's where I'm at so far. Now what I want to know is this positive, negative, sine or cosine, and what's the period? Right? A couple things I'm seeing. I can see my period here maybe just going from peak to peak. Maybe that's my easy locations to see it. And then I look down and I'm like, oh crap, I don't know what those actual values are. Maybe those weren't such a good place to see it. Maybe I can instead see it as it's like the beginning of this cycle, up, down, back up again to the beginning of our next cycle. Well, it looks like this guy right here is our period is only 1 pi, right? Oh, you're right. Thank you. Getting my corrections here in chat. Thank you. Our maximum height is 7. Our midline is 4 right there. Cool. Now I figured out that our period is only pi. It's only half as long as we want it to be. So this tells me then that we should be looking at y equals, plus or minus 3. I don't know if it's sine or if it's cosine of, it looks like this will be 2x plus 4. I know it's 2 because this is going to say you only need to contribute half as much because our inputs are going to get doubled. So we therefore have half the period width right there. Now if you plug in 0 to pi, you're actually going to get the action of 0 to 2 pi because that interval got doubled. The last thing to consider is this a sine or a cosine graph? And is it the positive version or the negative version? Right? I'm going to say, since at 0 we do traverse through the midline, that suggests to me this is the sine graph. Right? Remember that cosine starts at its maximum. So at 0, we'd be at the top or at the bottom rather than at the midline right there. Right? By the way, I mean, I don't think there's anything wrong with you guys like marking. I mean, honestly, these aren't parts of the graph. Typically, we use dashed lines in lots of math graphing to indicate things like asymptotes and stuff like that, which clearly isn't what's happening here. I have absolutely no problem seeing these dashed lines on your graph. They really help us kind of visually see where the graph is. Since this passed through its midline rather than experiencing a max or a min at 0, I know it's sine, not cosine. But I'm also seeing that we're decreasing through the origin rather than increasing through the origin like sine normally does. So I'm going to say, but sine of x is increasing through the origin. Right, my stupid minimalist graph right there. We are decreasing through the origin, so we'll stick a negative on. So I think our final graph here is negative because it's flipped. And really the negative to me kind of is with the sign. And it's not like it's a -3. It's like a negative sign is the function. I like to kind of think to myself, rather than just there being two functions, sine and cosine, when I'm dealing with graphs, I think of there being four functions: positive sine, positive cosine, negative cosine. I think that that's kind of a good way to kind of visualize that choice right there. My negative choice was associated with my sine and cosine choice right there. So I'm thinking negative sine of 2x plus 4 right there, I think is the overall graph of this function right here. Right? And certainly you can go double check that in Desmos. You can see I've made this graph in Desmos and just took a screenshot of it right there. And exactly, now what I'm also seeing in chat is a way that we could rewrite this as a, one tiny difference with yours, Freeman. You need another set of parentheses on the inside right there, and that's why the horizontal shift is such a pain. Oh wait, no, you do have it right? Because it should be that we're doing sine or. Oh no, no, I still think that you do. I think that yours would be correct if you swapped it for cosine, or it would be correct if you added an extra layer of parentheses in here. What we're going to come to find is that we can also deal with some horizontal shifts here by doing like sine of 2x minus pi. This will shift us by pi, which will do the same job as the negative out front right there. And so with this, it would be actually like a 2 pi shift. And also, by the way, plus or minus wouldn't matter. Shifting left or right, we'd land on the same spot. So part of the annoyance of the horizontal shifts is it has to have the constant multiple factored out. But if you're just watching this video right now, ignore what I just said, because that's what we're going to actually talk about at length next week rather than this one right here. And that's why those ones are a little bit of a bugger, because we got to pay attention to the extra factoring right there, which is why it's going to be in its own section. So there we go. We got our graphs of sine and cosine. Your goal for this week is to be able to produce graphs like this by hand without help, or to be able to see a graph and for you on your own determine what function it actually is that's describing it. The reason we want to be able to do this is so that we can do actual, I scanned past it, so that we can do actual modeling, right? This is now a descriptor of a real world phenomenon of the temperature in the town that we live in. This is valuable stuff to us right here. So in our next couple of classes, we're going to look at some more graphs. We're going to look at our tangent, secant, cotangent graphs. We're going to look at that complicated shift stuff that we were just looking at down there. And we're going to see some of our real world modeling applications. Those are really like the three big things that we're going to see next week, is like applying this to actual scenarios rather than us just like doing math with x's and y's, actually talking about like temperatures and times and other things like that that vary sinusoidally out there, right? So there is our wrap up to our introduction to graphs here. And that is our wrap up to our week 3 things. I will see you guys for section 6, 8, and 6, 7 in that order in our next week's classes out there. So thanks for being in chat, everybody, and I will see you guys next time. Have a good one.